Over the past 2 years, the Purdue Data Mine team has teamed up with Boeing data scientists to explore cybersecurity defense solutions for avionic networks, as well as raise awareness for avionics cybersecurity at the college level. This endeavor was born from a shared recognition of the increasing vulnerability of modern aircraft systems. This initiative lets students develop a digital twin or a sandbox of an avionics domain where they could brainstorm potential attack vectors and craft defense strategies. The culmination of these efforts was a presentation at the AIA SciTech 2024 conference, where the team shared their research with aerospace professionals. The project was positively received, and the team recognized areas where they could enhance their research. For starters, they wanted to increase the fidelity of the digital twin and integrate a new attack vector related to the automatic dependent surveillance broadcast, also known as the ADSB, an advanced surveillance technology pivotal for aircraft ATC communication. Addressing potential spoofing vulnerabilities in ADSB has now become a focal point of the team's endeavors. To increase the fidelity of the digital twin, they decided to implement a data bus protocol. They were originally going to implement the A-Rank 629 protocol, but since that wasn't easily accessible to the public, they decided to implement the military standard 1553 instead, which is just an older version of the A-Rank 629. The data bus system defined by this standard is comprised of one bus controller that controls multiple remote terminals. All communication throughout the network is managed through the one bus controller. The bus controller must initiate each transaction. In the digital twin, there is only one data bus system present in the aircraft control domain. The flight control system acts as the bus controller, while all other systems are classified as a remote terminal. Utilizing Python, they wrote a library that replicates the protocols present in the transactions between the remote terminal and the bus controller. They were able to integrate this library into their current digital twin model. Now, currently, an aircraft's ADSB has no protection in place to handle spoofing attacks, which are attacks where someone or something pretends to be something else in order to gain access into a system. Because of this vulnerability, an individual can send a false ADSB message to an aircraft. The message could contain information about relative position and trajectory, and therefore could imply a future collision. To defend against this, the team proposed a check using the received ADSB message's signal strength. This received signal strength can be used to calculate the distance between the signals and the receiver. This distance is then compared with the location indicated by the decoded ADSB messages. These calculations can verify the message's authentication. In the digital twin model, the false ADSB message is recovered in the offboard ACD, then sent to the aircraft navigation, where it is verified using the RSS check. The decoded ADSB message, as well as its validity, is then sent to the electric flight bag. The pilot, upon receiving this data, can make their decision on how they want to respond in the flight control. Thank you so much for listening. If you want to hear more about this, we encourage you to come see our poster at the Data Mine Symposium this month.